Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of losses of head due to sudden contraction. In our previous lecture, we already have discussed regarding the losses of head due to sudden enlargement. Now we'll discuss about sudden contraction. So for discussing this losses of head due to sudden contraction, first let me give a brief about this topic. So we are discussing about the losses of energy. So the losses of energy nothing but also known as losses of head, and the losses of energy is divided into two categories. One is major loss, another one is minor loss. So major loss already we have discussed, this is due to the friction, and minor loss used to happen so many regions are there. So this is one of the region of the due to sudden contraction in the pipe. So sudden contraction means let me consider there is a pipe flow is there. So the liquid is flowing through this pipe, and which of a diameter of suppose d1. So let's consider this is the diameter of d1, and now when it is moving and suddenly it was changed its diameter. Now you see this is the after this is the d1 diameter is there. Now suddenly its diameter is changed to d2. Okay, another one pipe diameter. So this is we can consider d2. Now at this d1 or the pipe one here, okay, we can see if the pipe is continuously moving, suppose the same diameter is moving, then we can see the flow is like the fluid is covering all of the surface of this pipe. Okay, it will be moved with the fully developed, or we can say it is moving with by connecting with all the surface of the pipe. But when suddenly these changes happen in the pipe, the sudden changes happen in the pipe here, so we can see the fluid also it's changing its path. Okay, the fluid also is changing its path to a new form. Now you can see how it is moving. It is moving like continuously. It is goes on decreasing mode. You see, initially it was in like at the same from full surface it is flowing. Now if you see when it is sudden contraction happened here in the pipe, okay, the fluid also is changed its path. It goes on decreasing mode. It goes on decreasing. So up to a level it will decrease its flow path, and after that again it enlarges. Now you can see it again it enlarges here. So this path, this zone is called this CC zone, where we can see the minimum surface area of the fluid flow. That is called your vena contracta. That is called vena contracta, where you can get the minimum surface area of the fluid flow, and after that it expands again. After that it enlarges. Okay, and it enlarges to the smaller pipe. Now here, to understand this concept, we need to consider two different sections. Section 1, this is section 1, and another one is section 2. So these are the two sections up there. Now try to understand why this due to the sudden contraction, how the losses happened actually. So if you see this flow, now it is though the flow of the area is reduces, but after going some level again it started expanding, or it started enlarging. So if you now, as I told you, this is the region of vena contracta. So the loss of head due to sudden contraction, actually is due to the sudden enlargement. So this HC is nothing but, as I written here, SC is nothing but the head loss due to sudden contraction is actually due to the sudden enlargement, which we already have discussed in our previous lecture. Okay, and also you can write the head loss due to sudden contraction is equal to the head loss due to the enlargement plus the head loss up to the vena contracta. So these things need to be considered actually. So to find out this equation, or to find out this value, we need to go to the previous our derivations, where we have derived the head loss due to sudden enlargement. So before going to that, let me tell you what are the notations are there here. At the section 1, we need to consider what P1 is there, the pressure intensity at this is the section 1, and this is section 2. So to derive this equation, we need to consider section 1 and section 2, two different sections. And in middle, again one more section came, that is Vanna contractor section CC. So anyway, what are the parameters are there? P1, A1 and V1. Pressure intensity at the section 1, area of the section 1, and V1 is the velocity of the section 1. Similarly, P2, A2 and V2. Pressure at section 2, area of the section 2 and velocity of the section 2. Similarly, also we need to consider at the CC point, also we need to consider what is the CC, velocity of the Vanna contractor section, and what is the area of the Vanna contractor section. Okay, these two things we need to consider. Now, when the flow is moving, actually you can see, as I told you here, what is the loss of head loss due up to the Vanna contractor. Head loss in the sense, when the fluid is moving in this way, so few liquids particles will be come out its original path and it will be moves to this side. Okay, but the fluid will be very high, you can say. The fluid particles will be changed its path and few particles will be come at this zone, and there some vertex formation will be there. Some vertex formation will happen, and due to this vertex formation, it will be create a impact of pressure to the fluid flow, and which is the major reason for the losses of fluid, we can say, or the losses of energy actually. So this vertex also creating a pressure on the fluid surface in this point also. So that's why what is the losses happened after the Vanna contractor need to be considered. So next is we need to consider here, we can write the HC. To find out the HC, first we need to identify the HE. HE we know that V1 minus V2 by 2G, this is whole square. This one we got in the previous equation, like previous derivation we got. Now this one we can write now. There V1 section was there. Now we need to consider a section HC from Vanna contractor to section 2. So that means we can write this VC minus V2 square divided by 2G. So this is what we'll do. Again, I'll just multiply V2 square here in the numerator and V2 square I'll divide here. Again, bracket we can start here like VC minus V2, this is square, this one you can give bracket like 2G. Okay, now here you take it to this V2 square inside, 2G outside, so you can write this is V2 square by 2G, and here we can write what the total VC minus V2 by V2 whole square, we can write it. Now again, if you write individually splitting it, so you can write this is V2 square by 2G, and in the bracket we can get VC by V2. So let's write VC by V2 minus V2 by V2. This is whole square again. So V2 by V2 is nothing but 1, and here we can write VC by V2 normal like this. So you can write this is HC equal to, see HC I have written, now I am writing HC because HC is nothing but the due to the sudden enlargement only. So you can write in this way also. This is V2 square by 2G bracket start, and this is VC by V2 minus 1 whole square. So this one we can give equation 1. So this is one region. Now again, we know that from the continuity equation we can write AC VC equal to A2 V2. Now previously we used to consider A1 V1 equal to A2 V2. Now our A1 is from here only, from the AC only. Okay, from the Vanna contractor only we are starting. So again we can write here what? We can write VC by V2 equal to A2 by AC. So in the place of AC by A2 by AC, we can write this 1 by AC by A2, I can write, and here I can put the value of this 1 by CC. So what is this CC? CC is nothing but the coefficient of contraction, or you can say that the coefficient of that contraction happened in the Vanna contract actually. So the CC is nothing but we can write 1 by, sorry, AC by A2. That means the area of the Vanna contractor to the area of the pipe. Okay, so you can write. So this is the equation. Now put this equation, this VC by V2, you can see VC by V2 is here, this one. VC, this is VC by V2. You put this equation here, so we can get, we can write what? Now HC equal to this is what we got there. Now V2 square by 2G, V2 square by 2G, bracket start, 1 by Cc minus 1 whole square. I hope whole square is there. Yeah. Now what we can write again, this point, this term, we can write k value. Okay. So what we'll get here? Now SC equal to k into V2 square by, again k is the constant term. So now we can write k equal to, depending on the Cc, coefficient of contraction. So this is whole square. Now actually, so if you put the value of Cc equal to 0.62, 0.62 I am taking. Now by experimental they found that the coefficient contraction value assumed to be near about 0.62. If you put this value, you can get like 1 by Cc minus 1 by 0.62, 0.62 minus 1, bracket start. So let's calculate this. 1 divided by 0.62 equal to minus 1 and square of this, so 0.375. So we got 0.375. Just put the value in this. So what we will get here? So we can write SC equal to 0.375 V2 square by 2G. This is one equation. When the Cc value is given, if Cc value is not given, then still also you can write, we can consider the equation SC equal to, they are slight different, 0.5 V2 square by 2G. Okay. This is all about the losses. So I hope you understand this concept. If you are having any doubt regarding this, you can give a comment on the comment box. So this is one equation. Also, we can mark it 2. This one we can give equation 3. And this is all about the equation regarding the head loss due to the contraction here. And I hope you understand this theory part. If you are having any doubt regarding this, you can give a comment. But this concept is very, very simple. Like we need to consider this, the vena contracta zone, because that is the most crucial zone. Though we are considering the sudden contraction, but again we are going back to the sudden expansion. Then from there we are taking this equation. Okay, this is the equation of sudden enlargement or expansion. So finally we got this equation. These two equations you need to remember. Thank you all.